Thank you so much for coming back. We promise to make it worth your while. For those that I have not met, my name is Songa Bavuba.
And my name is Margaret Conradi.
Welcome back from the break. We saw a couple of people having great fun during the break, but we'll mention that later. Thank you for the refreshment break sponsor, which is Communicate Recruitment, and welcome back for our final session of the day. However, before we move on to our plenary to close out the day, we want to share with you a quick interview with SA3.
Good afternoon. We're joined today by Wilhelm, Henda, and Yuri, three actuaries from SA3. SA3 is once again the platinum sponsor for the convention, and they've been so for the past 6 years consecutively, so quite strong supporters of the profession and the association. I must admit, your stand quite objectively is quite popular amongst the attendees and the children. So we'll be coming by and hope to get some goods there. Just in terms of some of the actuaries who may not know what SA3 is, could you tell us a bit more about it so that they can get a sense of who you are?
Ricardo, thanks. It's great to be back. For the sixth year. SA3, most people know us, but we're an actuarial recruitment business. And we connect people with each other. So we connect employers with the best talent out there, and we connect actuaries with great roles. I think it's safe to say that we've been the go-to team in terms of actuarial recruitment for the last number of years. And I think what sets us apart from other recruitment firms are the fact that we are 3 fully qualified actuaries on our team. The other day we counted, we have about 30 years of industry experience between the 3 of us, and another 45 years of recruitment experience. So I think that combination allows us to really understand job specs and understand the technical side of recruitment. But also I think we've become quite good at recruitment as well.
Yes, one of the most rewarding aspects of what we do is that we see how people grow. We place junior students initially, and then years later, they return to us, this time as managers, trying to recruit for their own teams. It's a wonderful full circle moment that speaks to the trust that the actuarial community has for SA3. It's something we are truly grateful for.
Awesome, excellent. No, that's fantastic. And I think it speaks to both sides, the employer and the employee aspects that you guys get so well. Just in terms of the program, you guys have a session on Thursday on employment equity targets, which are sector specific with an actuarial lens and a South African lens. Can you tell me a bit more about it?
Yeah, Ricardo, we'd like to invite everyone to the session. It's a session where we do a deep dive into the financial services sector targets. It's a topic where many of our clients have reached out to us and said, listen, how do we do this? Can you give us some guidance? How do we implement this? So the way we did it is we ran a survey amongst all our clients, and in the session we'll be sharing our results and insights of the survey. Yeah, I think it's going to be exciting. It's on Thursday tomorrow at I think 2:25 in the Ballroom 150. Yeah, so I want to ask people, don't miss it. It's going to be the targets impact everyone, and I think if you attend, you'll find it interesting, and it's going to be fun.
For sure, and I think it speaks to our theme, beyond the numbers.
Beyond the numbers, absolutely.
What happens in society. Yuri, just bringing you in your app, a lot of actuaries use it, engage with it. Can you tell us a bit more about it?
Great, thanks, Ricardo. I think our app has really taken off in recent years. We're up to, I think, about 3,500 downloads at the moment, or nearing that. So that's really great. And I think what we've tried to do is listen to feedback that we've been getting, improve the app each year. So for anyone who hasn't downloaded it yet, I think take it as a sign. And then in terms of the highlights from the app, I think I want to highlight 3 things. Firstly, the salary survey. So you'll find that on the profile tab. It's a yellow block. You tap on that. It takes a couple of minutes to complete it. Our salary survey, it's a 10th edition this year. Our donations are going to High School Bonnievale, 250 Rand for each person that completes the survey. And just to improve, education and opportunities for the local youth in that community. We've got big aims. We hope to get up to 450,000 Rand in donations to the school. And then for each person that completes a survey and they come to our booth and shows us their screenshot where they've completed it, they can get a special gift. We've got like you were saying, a great booth with some special gifts. Two other tabs that I just like to highlight, the vacancies tab. So on there, you can just find information about actuarial opportunities from entry level all the way to executive. And then the schools tab, where you can see what partner schools we've been working with, what projects, and how you can get involved yourself.
If I can maybe just add, there is I think our salary survey has become a real industry benchmark over the years. I mean, from where we started now, we've got more than 1,500 respondents last year, and this year we're on track to beat that comfortably. So we're very excited about that. Yeah, so like in the past, everyone that contributes to the survey, will get the detailed report afterwards, and it's always good reading. So yeah, again, we would like to encourage everyone, please contribute.
Thanks, excellent, and I think you're right. The app has become an industry standard and benchmark for salaries and increasing transparency and awareness amongst actuaries, and the financial inclusion aspect, which is quite great. For actuaries out there who may want career growth and explore opportunities in the market and would want to be guided, how do they get in touch with you guys?
We've made it easy. Come visit us at our booth here at the convention. The stand looks amazing, and Liddell has really done a wonderful job again. And thanks to our new confectionery partner, 108 Peaks, we have some extra sweet treats for you this year. Please come and say hi. You can also download our app. That's the quickest way to make contact and also keep up to date with the vacancies and surveys. Click on our website, www.sa3.co.za, or simply reach out to us via phone, email, WhatsApp, or even LinkedIn.
I mean, we're wrapping up. So from SA3 side, we'd like to just say thank you to Asa, and thank you to Keith and his team, and Casey and everyone. That it looks like really an amazing convention. So thank you for that, and thank you to the actuarial community for their continued trust and support over many, many years. We are really grateful for that.
And to all the attendees, enjoy the sessions and the networking, and remember to complete the salary survey.
Awesome. Thanks for partnering with us, and thanks for the conversation. Quite insightful.
Thank you.
Thank you.
Righto.
I now have the pleasure of introducing Dr. Luca Pontiglia and Yashin Modi to the stage. Universe on Stage is a vehicle for curiosity, where art, science, music, and storytelling come together to explore our understanding of the universe. Our goal is simple yet profound, to awaken that childlike sense of wonder, and for those who still have it, to remind them to keep it alive. Founded in 2022 by Dr. Luca, a physicist and speaker, and Yashin Modi, an actuary and composer, Universe on Stage began as an intimate performance for 50 people in a small cinema. It has now grown into sold-out productions of over 1,000 audience members in major theatres across South Africa, most recently collaborating with the Joburg Ballet. Together, Luca and Yashin bring over 20 years of combined experience in technical storytelling, the art of making complex ideas not only simple, but profoundly enjoyable. Please welcome them to the stage.
You should not exist. Is what I would say if we just looked at the numbers, the statistics that outline the improbability, the impossibility of the existence of life. At the core, life is composed of proteins, chains of amino acids that fold in different ways. Different folds create different functions. The smallest protein, the smallest set of proteins that life uses is just about a chain of 100 long. And the odds of randomly assembling a chain of 100 proteins that fold in just the right way is 10 to the minus 60. Take the forces of gravity and the electromagnetic forces that occur within the atom. They have a ratio so precise that if it was any different in the stars, the engines of the universe would not be born, and that ratio has to be precisely set to 1 part in 10 to the minus 40. Our universe has a sort of fine-tuning. The rate of expansion of the universe is astoundingly precise, to 1 part in 10 to the minus 53. And if it was any different, the universe would have ripped itself apart or collapsed into nothing. When we just look at the numbers, the statistics, the structure, the theories, the order of the universe, life should not exist. And yet, by us being here today, tells us otherwise. Somehow, life went beyond order. My name is Dr. Luca Pontiglia. This is Yashin Modi, and we are Universe on Stage. So, I have a background in theoretical physics. I did my PhD in string theory at the University of Witwatersrand, and Yash, as most of you might know, is an actuary. We both work at Discovery, and we actually met once at a competition, a Discovery actuarial conference, where Yash came to me and was like, I've got an idea about, disability prediction. Disability prediction. And asked me to help him to do something. So I'm working as a data scientist at Discovery. And so we came up with a model, and we ended up winning this conference, and we realized we work really well together. So I approached Yash because I learned that he can play the piano. I approached him with an idea. I want to try and talk about science in a way that's very unique. And I want to have music being played in the background. So at the first show, we had some Hans Zimmer pieces. Yash was playing a cover, and they started doing very well. We started realizing that people enjoyed this form of science communication. Eventually, I learned that Yash can actually compose music. So over the next few years, we ultimately built Universe on Stage as a vehicle to showcase that within the universe around us, there is an intellectual understanding of how things work, but there's also an emotional attachment to that. And we realize that it's the emotions that drive often our ideas forward. There is a story about Albert Einstein. He was asked, does he believe in miracles? And Einstein said, well, not really, not the way that most people believe in them. You see, most people think of a miracle as something that happens very rarely and no one can explain why. But to Einstein, a miracle is that we can explain the things that are happening around us all the time. As a scientist, as actuaries, we're often trained to predict the world, to understand. But how can we actually do that? What allows us to understand the structure of the universe around us? I believe it's because of two things. Naturally, mathematics. Mathematics is a language of logic, of structure. The universe, beneath its incredible complexity, lies structure. And so we as human beings use mathematics as a language to understand, to interpret the structure of the world around us. But we need also curiosity. Curiosity gives us the drive, the desire to understand why and how the world works the way it does. Take, for example, the story of Eratosthenes. He was a polymath, the head of the Library of Alexandria. And one day he comes across a book. And in that book, there is a story about a town called Syene. And there's a well. And at 12 o'clock on the 22nd of June, you can see directly inside that well. The light comes from directly above and illuminates the bottom. This only happens on that day, no other day. On top of that, there would be no shadows because the sun would be perfectly parallel to any columns. To most people, this would be pretty useless. But to Eratosthenes, who was a curious person, he asked himself, well, will the same phenomena occur in Alexandria? So he waited 1 year later, and on the 22nd of June at 12 o'clock, he went outside and he stuck a stick in the ground. He observed a shadow. Now, it's very curious. How could he explain that there was a shadow in Alexandria, but no shadow in Syene? Assuming the light was coming from directly above, at the time, the common knowledge was that the earth is flat. So you could easily explain how there would be one shadow in Syene and no shadow in Syene, no shadow in Alexandria. And you could also explain why there could be concurrently two shadows, the same one in Alexandria and the same one in Syene. But how then can you explain that there is no shadow in Syene and there is a shadow in Alexandria? This led to Eratosthenes coming up with that idea that went against conventional wisdom. The earth is round. It's the only way to explain what he observed. That the light coming directly from above is changing its angle as it hits the posts. Moreover, because he understood the geometry of a circle, he could actually measure the circumference. He knew the distance between the two cities. It was 800 kilometers. How did he know this? He got someone to walk it. Walked 800 kilometers. But with that in hand, he used some simple geometry and he calculated what the circumference of Earth had to be. And what's incredible is that he got remarkably close to within 99% of the actual number. And this shows us that with a little bit of mathematics, some curiosity, and a healthy appetite for experimentation, we can discover facts about our universe before we even see them with our eyes. Mathematics as a field had very humble origins. It began with numbers. If you were a shepherd, you would have to look after your sheep. You have to count them day by day to make sure no one was missing. You had to keep track of what was around you. As society became more complex, our need to describe, to keep track of things increased. And so mathematics developed. The philosophy, the field of knowing why things work, that was very separate to mathematics, its own field. But over the years, they got closer and closer, eventually combining with a single person, Isaac Newton. In the 1700s, Isaac was the first person to take the ideas of mathematics and philosophy and unify them in a single framework, the basis of the scientific method. He built structure and understanding of our universe using two ideas. The first was a force. Newton believed that everything in the universe is governed by forces. It moves because a force acted upon it, or it stopped because a force acted upon it. And to describe the force, he had calculus, the second idea. Calculus was a mathematical framework that allows him to describe the fundamental nature of how things change. And so using calculus and using forces, he developed understandings of our universe that we had not yet done. He developed gravity, a theory of gravity. a theory that was allowed us to understand the motion of planets and stars unlike we'd ever done until that point. It wasn't just gravity, it was the scientific method which Newton gave us, spreading in all fields. In particular, the field of what is at the smallest scale. You see, in 300 BC, there was a person called Democritus who was asking himself a very specific question. What is the smallest thing that exists in the universe? He supposed if I take a rock and I cut it in half, I cut it in half again, and again, again, how far can you go? He called it atomos, the indivisible. He believed that there was a point where you could no longer cut something in half. This went against his contemporaries who thought that the universe was made of earth, fire, wind, and water. The atomic theory of matter over the years persisted. It grew more rich, more structured. And at the end of the 18th century, we had a theory of the atom. We called it the plum pudding model. It says that the atom had little electrons inside a spherical shell of positive charge, like electron raisins inside a positive plum pudding. Ernest Rutherford was a physicist who was tasked to understand the structure of this atom. How dense was it? How does particles interact as they go through it? He set up a very simple experiment. He took a thin gold leaf foil. They knew the thickness. He took radioactive source, shooting positive, highly energized alpha particles. And it went against this beam. It's called a scintillator. Every time a particle hits it, it shines. By calculating the trajectory of these alpha particles as they go through the foil and how much energy it had as it sparked, they could understand the structure of the atom. Now, as theory suggested, the experimentation evidence that they saw was aligned with what they expected. Nothing really happened, and sometimes there was some scattering on the other side of the foil. But then Rutherford had a curious question. Well, what if I turn my detector on the other side of the gold leaf foil, the same side as what is shooting it, the source? All his contemporaries said it's a waste of time, you're not going to see anything. If you did see something, it would be like shooting a cannon against a sheet of paper and it ricocheting back. It was impossible to see what Rutherford was hoping to see. But he did it nonetheless. He observed and he waited. And then he saw something. He saw sparks. Sparks at almost 180 degrees directly away from the foil. It was rare, but it was consistent. And he realized that the atom had to have a very different structure. It had to have a very strong, heavy, positive core. Most of the time, the particles would go across. Sometimes they would be deflected. But every so often, they would hit and bounce back. This completely redefined our understanding of what the model of the atom is. It introduced so many new theories like quantum mechanics. And quantum mechanics then told us that actually an atom has what we call energy levels. Electrons can move up and down these levels, and every time they move, they emit a little bit of light. The energy these electrons have is dependent on the actual atom. And so what we get is that every atom emits a fingerprint. Different light comes out of different atoms and becomes almost as if like words, telling us the story of our existence. Because when you look up at the sky, at the cosmos around us, we can see what exists. We can see the light coming from the universe, and we can make it out based on these different lines. We can distribute. We can tell the distribution of the abundance of atoms. we see the hydrogen is the most abundant, and it moves downwards as we get heavier and heavier. The first few elements are created by something called primordial nucleosynthesis with the Big Bang. The slightly heavier elements, lithium and boron and beryllium, those are created through fission, when atoms are split in half to create lighter elements. But by far, the most common way to create atoms is through fusion. We have stellar fusion, the process at which atoms are made within the star that exists between carbon and iron. To make the heavier atoms, we need cataclysmic fusion. Fusion from incredibly violent and powerful sources. And when you look at life, we see there's about 26 elements. Just 26, which describe the full complement of life, of bacteria, animals, plants. But to understand how these elements came together to form all of us, well, for that story, we have to go back to the very beginning, when the universe was smaller than a grain of sand. Just after the Big Bang, there was something far more fundamental than atoms. There was matter and antimatter, fundamental particles which were in a sense mirrors of each other. The important point here is that when matter and antimatter collide, when they touch, they completely annihilate. All of their mass is converted into energy. Now we know from a very famous equation from Albert Einstein, E is equal to mc squared, that mass can become energy. But more important, energy can also become mass. And so the early universe was a hot pot of matter, antimatter, particles popping in and out of existence, colliding like droplets in a stormy ocean. But then, something happened. The universe suddenly expanded at a rate so fast that it took a sort of snapshot of all the distribution of matter and antimatter that existed at that instant. Most of it cancelled out. But there was a sliver, about 1 part in 1 billion of matter which remained. And it is that matter that makes up everything that we see today. As the universe expanded, it cooled slightly. The fundamental particles known as quarks combined to create protons and neutrons. And together with the electrons, we now have the ingredients, the building blocks of an atom. But we would have to wait 300,000 years for that to occur. For until then, there was a sort of waiting game, a dance between the protons, the neutrons, and the electrons, all trying to come together, to merge, but being flung apart over and over again from the residual heat and energy after the Big Bang. But the universe kept expanding. It kept cooling. It eventually reached a size that it was around 1,000 times smaller than our own universe. And yet, it was still so dense. Light couldn't escape. Photons were bouncing around, colliding with electrons, like headlights caught in a thick fog. But eventually, after 300,000 years, the universe cooled just enough for the protons and the neutrons and the electrons to finally come together, to merge, and in so doing, forming the first atom. They formed hydrogen. All of the hydrogen we see today was formed in that instant, like soil being turned over, ready for the garden of the universe to grow. In the moment the electrons and the protons and the neutrons combined, light was able to escape, like the fog being lifted. But what followed was darkness. 100,000 years of darkness. Dark, but not silent. All this hydrogen gas which is now being created is spreading throughout space as it expands, rippled with tiny fluctuations of slightly more dense gas in different regions. Those regions with more mass means they have more gravity. More gravity means more attraction of the surrounding gas, which pulls it inwards. And over millions of years, this process creates a small nodule that gets bigger and hotter, until eventually it gets so large that the gravitational pressure is pushing along into the protons, the photons. All the atoms combine, fusing, giving birth to a star. Stars exist because there is a balance between the gravitational force, which is pushing inwards on all the mass, and the output pressure created by the thermonuclear explosions of the hydrogen atoms fusing together, multiplied over billions of them. And it is in that balance, in the tension, which stars exist. The early stars of the universe, enriched with so much pure hydrogen, grew scales that we could not imagine. There is no star today that even comes close to the size of these early titans. For as long as stars have hydrogen, they will burn. Small stars will burn for billions of years, and large stars will burn for just a few million. But no matter the size, they all eventually come to the same end. The hydrogen starts to run out. A runaway fusion occurs, expanding the outer surface of the star. It grows bigger, inflating. It reaches to a point that we call a red giant, engulfing everything that lies in its wake. One of these stars, where our sun is, would envelop our entire solar system. And yet, when the last bit of hydrogen runs out, the outer surface will collapse and the universe shudders. When a star dies, the outer surface will rush inwards at almost a quarter the speed of light, striking the inner core and creating a momentary explosion so bright, so powerful, that it will outshine the very stars in the galaxy it finds itself in. It is called a supernova, and it creates a momentary display of color energy, like abstract artworks of the cosmos. In the moment that the supernova occurs, there's enough energy, the cataclysmic fusion begins, fusing heavier atoms. But importantly, it scatters them, spreads them throughout space, mixing with the surrounding hydrogen gas. And it allows for the second process to occur. Now that we have heavy atoms, they can split through fission. But what we need are neutrons. Neutrons, when they collide with an atom, it'll break it in half, making them smaller. And there's no greater source of neutrons than a neutron star. Sometimes when a star dies, when it's big enough, there is some matter that remains, too heavy to fuse, but under the gravitational force, the protons and the electrons actually come together, combining, forming neutrons. One atom after the next, a big mass, the size of a mountain of neutrons occurs, but can have the weight of an entire planet, often spinning itself at almost speeds of that half of the speed of light. These neutron stars are like bombs, waiting for a detonation event, often in the form of another neutron star, created somewhere else in the universe. They somehow get trapped in each other's gravitational orbit, getting closer and closer. Eventually, they collide. And in that collision, it is like a shotgun of protons scattering throughout space, colliding with those heavier atoms which were fused in the stars that birthed them before it. We now have a space of hydrogen, but mixed with all these heavier elements. That mixing, once again, creates clumps of heavier regions, more gravity. But this time, stars are not forming. We have a whole different process entirely. We have planets. And what is amazing is that some of the elements that we find in planets needed stars to die twice for them just to exist. When a clump forms near a star, the heat shifts, changes its nature. Most planets begin by having a heavy core with gas plumes around them. But when they're near a star, the heat actually strips the outer gas, leaving behind a rocky core. These are the seeds of Earth-like planets. As we move outwards, where it gets a bit colder, we have icy cores. Around them, big gas plumes. These are our gas giants. All the planets are created along some invisible heat line, dictated by the very star which birthed them. Often stars and planets, they might begin in a very tight space. But as the universe expands, they often seem very alone, lost in the darkness of the void. In fact, stars are often so far away from each other, so distant, that we need a whole new measure just to capture the cosmic scales. We need to use time. We look at the distance traveled by a light in 1 year. Light is the fastest thing in the universe. It will travel around our Earth 7 times in 1 second. But it will move to the nearest galaxy, to the nearest star, in 4.5 years. But despite these vast distances, stars are not truly alone. As we zoom out, we realize they form part of cosmic cities of light, galaxies. Galaxies which are often hundreds of thousands of light years across, all held together by the hand of gravity. The early galaxy is chaotic. There is no way that life could exist. We have the elements, we have the galaxy, we have the home, but the conditions are far too violent. We have stars being born and exploding in mere millions of years. Neutron stars colliding, scattering high-energy particles. How can life possibly exist within such a space? You see, life is patient. She takes billions of years for her roots to take hold, stumbling and falling and trying again. In a universe where stars are seemingly only existing for a few million, there's just not enough time It would be like asking for a germinating oak tree to grow in a field trampled by elephants, battered by hail, scorched by fire. It seems an impossible contradiction, unless something intervenes. Something with enough power to not just control the chaos, but to calm it. And it so happens that it is through the chaos, through the destruction, the universe provided the answer in what we call black holes. Black holes exist because a large star dies. The largest of stars, when they collapse, they puncture what we call the fabric of space and time. And they create an immense gravitational well, a disturbance so immense that if anything gets too close, it can't escape. It has a boundary. We give it the name event horizon. And if you pass that boundary, even light, it is trapped there forever. More so, anything that goes into the black hole makes the black hole grow larger. Black holes grow when they eat matter, when they combine. And the largest black holes exist where you have the most amount of matter. And where do you have the most amount of matter? At the center of a galaxy. At the center of every galaxy, we find what we call supermassive black holes. Black holes that are billions and billions of times larger than the largest star that we know. And when these black holes are feeding off the neighboring stars, they give rise to a process which is, by no exaggeration, the brightest and most energetic source of energy in the entire universe. Quasars. They give rise to powerful beams, jets that emerge from black holes, stretching hundreds of thousands of light years in length. These quasars, the brightness that they emit is brighter than if we take thousands of the brightest galaxies with billions of stars and compress them into a region smaller than our solar system. And when quasars are created, they emit an echo of energy that goes throughout the galaxy. And it removes, takes away any remaining hydrogen gas that was just sitting there, idle. Gas that would otherwise have been used to form very large stars. Supermassive black holes at the center of galaxies are the regulators of star formation. They promote small, boring, ordinary stars, and they reduce the number of heavy, big, burning stars. They allow little stars to burn for billions of years. Stars that give us a pocket of time to give life a chance. And it just so happened, around one of those ordinary stars, life took that chance. At the edge of a spiral galaxy, which we call the Milky Way, we found an ordinary star, small. And around that star, there were 4 planets made of gas, 4 planets made of rock. And around one of that planet, we found our home. We found Earth. We found atmosphere. We found ocean. We found underwater volcanoes. We found inorganic molecules. And then one day something happened. One of those molecules split in 2. We don't know why or how this happened, but we know it did. In that moment, that molecule split, that bit of RNA split, our evolutionary clock began. Going from there to the complexity of life that we see today. But how did it do it? How do we go from a simple RNA cell, protein, to what we are today? It's because of 2 things: replication and mutation. Replication is the process by which these RNA molecules, which then eventually become cells, split themselves. They share the information from one copy to the next. Information encoded in the genes, the DNA. And importantly, whenever they split, they mutate. They alter the information ever so slightly so that certain species with the right amount of information can adapt to the changing environment. Mutation often occurs because of this error within the replication. But sometimes it's because of something far more cosmic. On every star, on our sun, you sometimes have these ejections of solar winds, powerful rays of energy move projected across space. Often they come towards Earth, perhaps wiping out life. But because of our magnetic field, it slows those rays down, protects most of life. And sometimes those rays will pass through less energetic, and they will reach our DNA. They will interact with the chemical composition and change the structure ever so slightly. In so doing, mutating. It is this process of replication and mutation that life was able to evolve from a simple DNA molecule to us today. by combining chaos to the order of the universe, life was able to evolve, to explore, to exist despite the overwhelming odds. And we are part of the universe. The same principles lies within us, within our ideas, within our creativity, within our ability to so often do the impossible. And so, next time the numbers, the statistics tell us something can't be done, maybe a little chaos, a little imagination, a little curiosity will allow us to go beyond and do the impossible. Thank you. Thank you, thank you. A big round of applause to Yash. Thank you, thank you, thank you. Thank you. So, thank you, thank you. So we do sometimes allow some questions. The questions can go from anything from science to music to maybe some more information about us. If I may, we have one slide that actually just talks about a show that we have upcoming. I'm just going to leave it on the screen if we can. There we go, perfect. So just a quick interjection. Yash and I are actually performing at the end of November with the Joburg Philharmonic Orchestra. And it's a 32-piece orchestra with music composed by Yash. For the first time, he's never done things before, but it's going to be incredible. And we're calling it the Black Hole Symphony. It is 6 short stories about black holes, what they are, and what they can do to transform our future. So I'll leave that there, but in the meantime, if anyone has questions, please, we have about, I think, 10 minutes, more than welcome to. So I think, are there mics around?
Yeah, there's some standing mics. So can I ask gentlemen in the front, will you go to the standing mic? Thank you.
Okay, perfect. There we go.
Thank you so much. That was amazing. I once read a book called The Quants about some mathematicians in the United States, just pre-2000, post-2008 market crisis. Can you, whatever you're doing here, can you build it and not a trading model? And let's see if actually it can work out. Amazing stuff, guys.
Thank you, thank you. There was more of a comment that maybe we can make money. So if we do, I'll tell you. Any other questions?
Any other questions? It is quite bright up here, so I might not be able to see your hand.
I can't see. If there are questions, you can just walk up. Otherwise, me and Yash will be around for a bit. You can ask us anything you would like.
Perfect.
Cool.
Oh, there's a gentleman in the back.
There we go.
Hello. Hi. So I've seen some crazy numbers about just how big the universe is.
Yeah.
Are you able to put into context as how small, say, an electron or a proton is?
So the question is, so how, we often talk about how big the universe is, but how small is the small, right? If I recall the numbers correctly, if we look at the distance of, so an atom has a central sort of nucleus of protons and neutrons, and you have the electron orbits that go around it. If we were to put, and it's a couple of orders of magnitude off here, but if we were to put a nucleus, which is the size of about a basketball, the orbit of the electron, I think, would be by Jupiter. So relatively speaking, they actually are very far apart, but also very small relative to each other. How to put it in perspective of how small it is, I don't have something on hand. I always actually talk about the big universe, not about the small universe. But there's a cool stat that so one of the Nobel Prizes a couple of years ago looked at the decay, the rate at which electrons move in these orbits. And that can kind of put into perspective, something in perspective here. So these electrons will move so quickly. They're called, I think it's Attoseconds, yes. So an attosecond is the time scale that happens within an atom. There are more attoseconds in a second than there have been seconds in the 13.7 billion years of the universe. And these electrons will move in a couple of attoseconds. So you can think about like the time scales that happen in an electron, an atom, are just wildly larger than what we experience as human beings here in the universe. So there's this like massive disproportionate relativity of scale and of experience of time, and it's quite phenomenal. I can try to think of better examples, but I don't have right now.
Thank you.
Thanks.
Hi, guys.
How's it?
So just a quick couple from me if there aren't too many questions. So the first one is just, at the beginning you talked about the balance of matter and antimatter.
Yes.
So do you perhaps have any insights into why that sort of balance fell apart such that you suddenly had more matter than antimatter?
Okay, so what's very interesting is, okay, we are familiar with matter. So matter is everything we can see, taste, and touch, all right? Antimatter is literally the same as matter, but it's called the mirror opposite. So for example, an electron has negative charge. A positron, which is the antimatter particle of electrons, has positive charge. But everything is the same. So if we lived in a universe of antimatter, we wouldn't know. Everything interacts just the same. So there is no distinction in the physics, in the way the universe would evolve if we were made of matter or antimatter. So it's the first thing to sort of note. It just seemed to be random. So when the universe was very small, we had quantum effects which were really ruling everything. So scales of the universe often give rise to certain laws which dominate certain scales. At the small, it's quantum mechanics. And quantum mechanics is ruled by fundamentally randomness. We had these antimatter and matter particles popping in and out of existence quite randomly. When they popped, they would annihilate and then come back to energy. If I am just splashing on a pool of water, maybe that's got like red ink and yellow ink that can't mix. And I just splash, 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 and I just take a picture. At some point, you will have maybe some variation of the white, of the yellow water versus the blue. And I think it was just random. We have a theory called inflationary cosmology, which tries to explain why that actually then formed the universe as we see it today. But the best we can say is that it was just random chance. And that's, again, so crazy how like 1/billionth that of this distribution made what we made today. And if it was any more and any less, then the gravitational interactions and the expansion of the universe would have mixed things up, so perhaps life wouldn't have existed. And so it kind of follows on to this different idea, well, maybe there are other universes. Maybe we're not special, we just exist in the universe that allowed for existence to occur. It's like a very small sort of point to that, and we'll go to the next one. If you look at Earth, right, our distance to the sun, people often thought there must be some formula to explain why is it that we're exactly this distance from the sun and we're orbiting at this ratio and we tilt at this thing. You know, it's so perfect. How could it possibly be? Well, when we realized that there were trillions and trillions of stars, each of them with different planets, statistically speaking, at some point there will be one planet with just the right variation so that life could occur. And so they often use that idea the same with universes, that perhaps there are trillions and trillions of universes, all of them with different variations, different statistics. Those collapse, nothing occurs. We just happen to be in the one that actually made it. It's called the multiverse hypothesis. We don't know how to prove it, but it's kind of like sort of speaks to that, what you were kind of asking. A bit of a tangent, but yeah.
Sorry, can I stop you there? I just want to take the last question in interest of time. Can I ask you to chat him afterwards? Thank you so much.
You can find me afterwards, thank you.
Hi. Can you hear me?
Yes, perfect.
So yeah, I hear your probabilities, and I see the maths, seems crazy. But if there's a theory that when you die, you have no sense of time, no sense of longness, no sense of a feeling, so 300 billion years, or whatever random number, seems like an instantaneous, instant, because you have no sense of time.
Yeah.
So we talk about probabilities as being impossible for humans to interpret it, but if we wait in 300 billion, 600 billion, all the simulations, all the possible combinations, eventually it's going to hit. So it's actually 100% certainty that life will occur given the simulation.
It's the law of large numbers.
So, yeah, I mean, so just because we can't comprehend the number doesn't mean it's certain as such. So that's just one thought. I think what I want to end on a bit of a more positive note is that, I mean, what is quite powerful is that we're in a state of self-awareness. And I don't think being human means you self-aware. I think any sort of particle, any sort of being that is reacting to psychological effects or anything non-physical has self-awareness. So when you're reacting only to physical things bumping into you, you're robotic and you have no self-awareness. So the point is that if you're self-aware, you're able to change your future. You're able to change the way things are going because you don't need physical effects, to change. So we actually have free will and we're actually developing the simulation because of our reaction to it. Which I think is quite powerful, and it just makes us maybe need to appreciate life because, we might not be in the same simulation or in the same form. We might be only moved by physical, sort of attributes. So I just want to sort of just say, everybody, what carpe diem, seize the day. Thanks.
Thank you. No, for sure. I think just as like a closing comment to that, I think there's the law of large numbers says that things that don't happen often happen all the time. And that's kind of also kind of the point, is to say that if you wait long enough with enough chance and chaos and everything happening, interesting things occur. But it doesn't take away from the astounding nature of it. That there's so many things that happen to happen just the right amount of time and the right chain of events, and we're just the end of that. The way I see it sometimes is that we're just a speck, right? A little bit of dust perched on the mountain of creation. But we are perched so perfectly that we can witness the entire scale of it. That was dramatic. And the point is to say there's philosophies, there's assumptions of why the world is the way it does. But I believe that if, as human beings, we can just be a bit more curious and we can sort of explore things with an open mind, we can make discoveries that really change things. And as Universe on Stage, that's exactly what we're trying to do. We're just trying to bring the science to people in a way that we currently understand it, to impart curiosity and wonder, that you can take it and do something with it in a way that changes your environment for the better. So on that point, thank you very much. Thank you so much for having us. And we will be outside.
Thank you so much, guys. That was incredible. Thank you so much. So this actually brings us to the end of day one of the convention. It's been really interesting. I mean, from starting with Trumpisms and the price of a McDonald's burger, and also knowing that we have issues with, wine, citrus, and the automotive sector based on tariffs, right? Right through to, I understand, talks about weight loss drugs that happened in another session, plus conversations about how we want AI to do our laundry, to a fascinating panel discussion we got to listen to about the national health insurance and how exactly, well, no one really knows how exactly, but what some ideas are for how that thing comes together or doesn't. As well as, I thought, some incredible research papers and presentation about demand and supply in healthcare, which was quite interesting, right through from neonatal kids through to people older than 65 and what that means in our world. And I saw another paper speaking about the importance of driving transformation in the profession through data. So I hope that everyone's found little nuggets of something spectacular today. If not, I think there may be sessions you want to re-watch if there's some that you missed. And we can't end today without saying thank you to the sponsors who have made this convention possible. I'm not going to do what Ricardo did in the morning. I'm going to speak slowly. Okay, and breathe in between. So we want to thank SA3, Discovery, Sapiens, WTW, Ernix, RNA, Analytics, Sanlam, Insight, Accurate, Genre, MBE Consulting, Piscal, I hope I pronounced that right, Liberty, Millman, Old Mutual, RGA, Swiss Re, Hanover Re, Software Alliance Limited, Colorfield, Africa Re SA, Communicate Recruitment, Network Finance, and IACA Consulting Actuaries. Okay, didn't butcher anyone's names, hopefully. We start tomorrow bright and early at 8 a.m. We'll head directly into the concurrent sessions. Obviously, you've got your program, your speaker bios, and papers available on the app. And if you are an early bird and here way before 8, there will be coffee from 7:30 so that you're more pleasant for the rest of us who'll arrive at 8. Next up, we want to continue having some fun. Maybe only half as much fun as I saw some of the gents in the room having on that Formula One simulation. I tell you, if you missed it, a certain gent, I won't call him out, almost fell out of the chair, is how hard he took that corner in the simulation. So we're going to continue with some fun. Next up, we have the Laugh and Linger Longer with an incredible comedian, Celeste Nduli. She'll be performing here in Ballroom 150. But before that happens, you get to go out those doors, grab a drink and a snack just outside of here, and make sure that you're back and seated by 6 p.m. So that gives you about 15 minutes. To make your break even better, Colorfield has sponsored the convention with a limited number of the hottest socks, yes, I said socks, in town, so make sure you don't miss out. It is a first-come, first-served basis, so right now we're watching those people by the door. It is a first-come, first-served basis. As Colorfield would like to say, every goal deserves its perfect fit. So enjoy Celeste Nduli, enjoy your Colorfield socks, and enjoy the Linger Longer. Those who are leaving straight away, enjoy Sandton traffic. Have an amazing evening, and we'll see you bright and early tomorrow at 8 a.m. Thank you so much, everyone.